So this is the second lecture about loop integrals and differential equations. So I just remind you that this morning I just was chatting to someone, we said we had 0 loops, because why is that? Well, because we were just looking at the functions which could come out. And I remind you, we focused on the function Li2, and we saw that it's kind of convenient to think of it as embedded into some vector where you start with a function and you have all of its derivatives collected together. And then we saw that it satisfies a very nice differential equation. Then in a second step, we also introduced some bookkeeping parameter epsilon in this way, which appeared then in this simple form, factorized form on the right-hand side of the equation, and that turned out to be useful as a bookkeeping device for counting the transcendental weight of the functions, but also then it was useful in thinking about solving the equations order by order in this parameter. Now in today's lecture, I'd like to connect this with actual loop Feynman integrals. So we'll see how for Feynman integrals, how such a vector arises kind of naturally without having, that you don't have to invent too many things. It comes out in a rather natural way. And then we'll see how we get differential equations, and then how, in particular, the differential equations will take some very nice form similar to this one. And then I'll also talk a bit more generally what kinds of terms you can expect here on the right-hand side. Before doing so, I'd like to start with a few comments about this, which I think will be quite useful. So let's start with some comments about these type of equations. So one comment has to do with discontinuities. And I want to point out that discontinuities of the functions we're considering, I'll define in a minute what I mean by this, but they are also solutions to the differential equations. And that will turn out to be quite useful insight later on. So what do I mean by this? Just as a reminder, we saw this morning that the functions we're considering are analytic functions in the complex S-plane. And I showed you that the logarithm has a branch cut on the negative real axis. We didn't really talk about it, but the same is true for this Li2 of 1 minus x. Now, what you can do is, we also saw that the integrals, we could think of them as contour integrals starting from some boundary point, for example 1, and integrating in this plane to some value which is our function argument. Now, usually we want to stay away from this branch cut, but one thing you can do is you can ask what happens when we cross the branch cut. And then, for example, the logarithm, it picks up some factor of, there's another term that you get, which is 2 pi I when you cross the branch cut. And what I mean by discontinuity is I'd like to compare the function just above and below the branch cut and take the difference. So that difference then for the logarithm would just be 2 pi I. And so that's my definition of discontinuity. So if we so for this function, I'm indicating the branch cut here, but really it's sufficient to do this operation to go around here, just around the pole at x equals 0. So we could define in this way the discontinuity of a function f around 0, and so what we would get is for the constant we get nothing because it doesn't have a branch cut. For the logarithm, so we'd get 2 pi I, but I'd just like to normalize things in a way that just becomes 1. And then for the dilogarithm, we get log of 1 minus x. And so now this is, if you wish, it's an exercise for you. You can convince yourself that this vector here if you replace f by that vector, it's equally a solution to this differential equation for the matrices A and B that we worked out before. And if you like, you can keep going. You see there's another non-trivial function here. If you want, you could take another discontinuity. Now, for this function, it has a branch cut rather starting at x equals 1, going off to the positive real axis. And so you could get a third independent solution here. All right, so that is one comment. Now, a related comment. So the discontinuities of these functions, they have to do really with the poles that we see in the differential equations. Because it's those poles that then sometimes they turn into the branch cuts. I mean, the location of the pole are potential branch points, and then depending on what the boundary information is, we may or may not have branch cuts. And so that's the second point. It has to do with the boundary behavior of the integral. Behavior and boundary conditions. And actually that's why this is very useful to think about it, because we said earlier that we needed some boundary condition to fully specify the solutions. So if we don't have them a priori, then it's sometimes we can actually understand them from some physical analysis of the differential equations. And for that, to really have the tools for understanding that, it's useful to think about these equations. So there's a couple of things to be said here. Maybe the first, let's start with some obvious things. So our differential equation, where does it have singularities? So we have singularities, at least potential singularities, if we look at the right-hand side of the equation at different locations, x equals 0, x equals 1, and that's sometimes not, one forgets about it, also potentially at x equals infinity. So if you like to, if you're unsure about this, then just think about a change of variables where you set y is equal to 1 over x, and you'll discover that you get a similar equation where you have then an explicit pole in y. And so through the change of variables, this tells you that there can be, that corresponds to x going to infinity. So that's already quite nice, because so then this differential equation tells us what's the maximal set of singular points that our functions can have. But now, how do the functions behave more specifically as we approach one of these potentially singular points? So there also the differential equations can help us. And now let me just take, without loss of generality, let us take x equals 0. So how does f behave as, for example, x goes to 0? So what you might guess intuitively is that when as x goes to 0 on the right-hand side, this is really the most important term, a divided by x, and in the first approximation, we could forget about the b term. So therefore, let's consider the approximated equation, dxf is equal to a divided by x times f. And by the way, whether or not I'm writing epsilon here doesn't really play a role. That's actually quite important to know that this analysis we're doing here, it has nothing to do with some limit epsilon goes to 0 or not. So for the moment, it's completely general. So if we now consider this equation, let me just put a little tilde just to indicate that's an approximation to the real f. Then this is something we can easily solve. So we can write f is, what is it? It's actually x to the a times some f0. So you can check if you differentiate that, that actually solves this equation. Now, careful, this notation hides a little something. Remember, F is a vector and A is a matrix. So we have here actually a matrix exponential. So matrix exponential means that there's a little bit of algebra to do when evaluating is. In the cases we had this morning, it's very simple because we have the nilpotent matrices. But even in the case of more general matrices, you can evaluate this. And typically what you get is you can have some terms which are explicit logarithms actually in this matrix. And then there can be other terms which depend on the eigenvalues of A. And that will be particularly interesting when we have the epsilon over here, because then you can get terms like, so this matrix exponential, let me now write the epsilon again. It can contain terms such as you can have explicit logarithms, but also you can have something like, for example, if there's an eigenvalue -1, you can have x to the minus epsilon. If there's an eigenvalue -2, you can have this, and so on. And this will then be closely related to some physical properties of your Feynman integrals. So I'm aware I'm jumping ahead a little bit, but I just wanted to mention these things. So for instance, these might have to do with soft, or this might have to do with some soft collinear regions of your Feynman integral. And so knowing this, and then comparing against what you expect physically from your Feynman integrals can sometimes help you to find a good boundary condition. More on that later. Maybe just one other word about boundary conditions. In general, when you think about fixing a boundary condition, you'd like to, so what does it mean? It means that you need to know your function f for some specific value of x. So you could say here in this example, well, what value of x should we choose? You know, if we were able to compute it. Maybe you'd be tempted to say, let's choose something safe. Say, I don't know, x equals 1/2 because the functions are finite. There's no, we stay away from the singularities. So that's very reasonable. However, the problem is then there's nothing special about that value, and computing the function at that value might be just as complicated as computing it anywhere else. So then what I'm saying is that there's a good chance that that calculation is not simpler than the general problem you set out to solve. As I sometimes like to say, physicists like to live dangerously. So the thing to do is actually go and select one of the singular points. That's where things get dangerous, but it's also at the same time you expect to see some simplifications. And so in general, I mean, this really depends on the case. What is the best solution or what's a good solution? But the general message is, do think about the singular values of your differential equation. And you might be lucky that some of the singular points, maybe although they're present in the differential equation, they actually allow you to gain some almost for free information about the functions. So that's kind of the take-home message. Consider the singular points of a differential equation in order to obtain boundary information. And in fact, in this morning's example, we did exactly this. I mean, of course, we had the answer, so it's a bit, it's not really true, but we did do this. And for example, this morning, we provided the boundary information at x equals 1. Now, what happened here, actually, it's quite amusing to think about it. You might say that was a bit strange because it's a singular point. How can we even talk about x equals 1? But you see, it's a singular point of a differential equation. However, the function f that we wrote down, it happened to be completely finite, regular as x goes to 1. Nevertheless, so why does the differential equation even know about this? Well, as you take a discontinuity, you get this function here, and that function now, that has a branch cut at x equals 1. So the function was finite, but still the differential equation, since we know not only about the function, but also about all its discontinuities, it already had to know about this special kinematic point. However, had we had some arguments in the first place to say, well, we happen to know from some ulterior source, from physics, that the function is finite at x equals 1, that would have given us free information to fix at least some of the boundary conditions. Okay, very good. If you have questions, feel free to ask them. I know this is maybe a bit abstract if you haven't worked with this. Why does the discontinuity have a dependency on x? Why does it have a dependency on x? Well, why does it have a dependency on x? Well, really, we're just you see. Let's go back to the original problem. So we said that we define these functions by some contour integral. For example, a logarithm that we start integrating from 1. In principle, if you think about the log as some complex function to some complex value of x. So there it depends on x. And now we're doing almost the same, except that we're taking this contour and we're going around the origin once, and then we go back to x. So it's fundamentally really the same thing, just that we are choosing a more complicated contour. Any other question? Yes.
So the fact that the discontinuity solves the same equation, is this a general fact about differential equations in complex variables?
How general is it? Actually, a good point. I'm just hesitating whether, in order to not to say something wrong. So I understand it in the sense that if you think about the symbol, the differential operators, they act on the right of a symbol, while the discontinuities act on the left. So from that, I'd expect that in general that they commute. So let's see if there's is someone here who will give me a counterexample on the spot. I think it's a pretty general property. Yeah. Mm-hmm. Yeah. I mean, sorry, just to say that it's actually a very good question. Specifically for Feynman integrals, it kind of follows from the way that we derive the differential equation. So there, I'm 100% sure. I don't know if one could think of some counterexample that's different. But I haven't thought about it too much, but I think it shouldn't be the case. Yeah, there's another question.
Yeah, no, I thought that discontinuity was a solution.
Mm-hmm. I mean, let me see. So I mean, really, it's about the commutativity. But okay, I could probably say a few more hand-waving things, but I'm not sure they would make the case clearer. So I prefer not to right now. Yeah. Mm-hmm. Okay. Was there another question here? Right. So we have a first order system of equations. So we expect that's when we talked about the boundary constants. That is, in order to fully fix it, we have to have n boundary constants. So in this case, n is free. So actually, so that explains why we have actually free. So this is another way of seeing that we have free linearly independent solutions, which is this one here, that one here, and then the final one. If we were to take another discontinuity. 1, 0, 0. Okay, very good. So the case of boundary behavior is really so interesting that I actually have another comment that I wanted to mention, which has actually to do with the nature of these singularities here. So in this system of equations, on the right-hand side, we always see at most a 1/x singularity. And that's actually something that we expect for Feynman diagrams. But you could have written something else. So what are the nature of the singularities? So we already saw that if we have this 1/x type singularity, then this is the type of behavior we get as we approach the singular point. And it leads to things that we indeed expect from Feynman diagrams, logarithms, x to some power in Dirac, and so on. Now, if you consider differential equations, sometimes you might find a different type of behavior. So consider now, for example, what happens if we have 1/x squared? Well, that's actually bad. Why is it bad? Well, this actually corresponds to some essential singularity. So we can see. So let's see what the solution would be. I think it's just exponential. I think it's exponential minus a/x, something of this sort. Let's just see. Yeah, I think that's right. So you see, in this case, we have an essential singularity. This is, of course, a function that's perfectly okay. However, it's not something that we expect from Feynman integrals. It might be something that could occur if we sum an infinite series of Feynman integrals, and then you get more complicated behavior, but it's not something that's expected from a single Feynman diagram. So not expected for individual Feynman diagrams or Feynman integrals. Okay, so very good. Does it mean then that we can never have a 1/x squared in the differential equation? Well, of course, the way I'm asking is the answer is no. Why is it the case? Well, there's a little trick. So actually, here secretly I've assumed that a is just a constant. But in general, A and B or in general, the right-hand side of a differential equation is a matrix, and that makes things a bit more subtle. And so this is related to the next point. So our differential equation system is not unique. So what does that mean? So let's say we have this equation over there, and let me just write it in a bit more general form. So let's say we have this form where capital A is some matrix which depends on X. Well, F is some vector. Now consider some invertible matrix, the matrix T. Well, then we could say let's define F to be T times G, where G is some new vector that we define in this way. Well, and now we can just do a little calculation. So df. So basically, it's just using the chain rule. So we get this expression, and on the other hand, it has to be equal to A times T times G. So we can equate these two sides. And then let's say we multiply by T inverse. I mean, T was assumed to be invertible. Then let's multiply by T inverse so that we can have dxg nicely on one side of the equation. So then what do we get? And I just write this here. So then we get dxg is equal to T inverse A t minus t inverse dx t, and the whole thing multiplies g. And so what we see now, sorry that that's kind of squeezed a bit at the bottom, we see that now we have a new matrix which we call B. So I'll just write this final equation here. So we have dx g is equal to B times g, where B is obtained from A through this transformation here, which looks a little bit like a gauge transformation for some. And the point is that here T, the only property the matrix T had to satisfy was that it's invertible. So you can imagine quite a few matrices like that, and let's say we make them rational, so that's quite reasonable. And they could really modify the structure of your differential equation quite a bit. And it would be easy to find in particular examples. So if you're given some little a, little b, you could imagine some transformation matrix T, which will now produce some double poles in X, or even some other poles at locations that maybe it doesn't have anything to do with a Feynman integral. So so that's quite interesting, and it's at the same time good to know about it, but it can also complicate our life because it's anticipating that we want to use this method for Feynman integrals, even if we expect that in the end we'll be able to have a simple form like that. This may be hidden. It might be obscured by some transformation T that we might have to undo. And the good news is that there's some hope. There's some ways of dealing with this problem. So just to be clear, from our expectations on Feynman integrals, it is expected that we can make manifest the set of singularities that the Feynman integrals actually depend on. And as you approach any of the singularities, you could find some matrix T such that it becomes manifest that it's only a single pole. Because eventually, all the other poles and all the other like double 1 over x squared behavior is just spurious, but it may not be obvious. Okay. Now my last comment is kind of also related to this, is related to this non-uniqueness. So if you don't like this non-uniqueness, there's actually one way of getting rid of it. And this is to say, well, this nth order system of equations, this system of n equations, we equivalently write it as a single equation, but a higher order equation. And the viewpoint would be that we constructed this vector to analyze the function Li2, but why not consider directly an equation that Li2 satisfy without these auxiliary integrals log x and 1? Because after all, we constructed them just to have this system. And if this system now has this gauge redundancy, as Jake would say, then maybe we don't want to consider these other integrals. Let's just focus on Li2. And sometimes that's also a valid viewpoint and can be very useful. So so there's an equivalent higher order equation. For one of the integrals. So in application to our example, we could do that for Li2. So it's really simple to do it here, basically because of the fact that our equations are nilpotent. So what would it be? So if we start differentiating this Li2, we can see what we get on the right-hand side. And if you remember, the first factor we got was some 1 over 1 minus x. So I just cancel it here. And then what we were left with was a logarithm. But then we know how to deal with a logarithm. We differentiate it. We get 1 over x. We take care of the x. Now we have the function 1. So we differentiate that another time. And then we have a nice higher order equation. So if you wish, this is an alternative form of phrasing our equation where we don't have this redundancy because we immediately just apply it to this highest weight function that we're ultimately interested in. So sometimes this is also in the physics literature has some names. I don't know if it's actually the proper name, but sometimes this is called Picard-Fuchs equation. And my mathematician friends would sometimes call this the annihilator. This differential operator they would call it the annihilator of the function Li2. Okay. Yeah. And here, if you wish, we can of course see the same properties. I mean, the singularities are now encoded in a slightly different way. We could replace this Li2 by its discontinuities, and again, they would satisfy the same equation. So it's just a different way of packaging the information. And as I said, sometimes this is quite useful. Okay, so now let's proceed with the. We're almost ready to proceed with the Feynman integrals. Yeah, sure. Yeah. I mean, there's at the system of the linear system. I mean, it's not arbitrary in the sense that there's something to aim for. So you could ask if you. So I argued that actually what we'd expect is that each singularity should at most have a 1 over x pole. So if the singular point is x0, then you expect 1 over x minus x0. Now you could use that expectation and ask yourself, is it possible, given some other form, to systematically make that manifest? And this is something that people have studied. There's various algorithms actually in the going back to the 60s in the math literature, and also more recently, and quite useful algorithms by people in the physics literature that investigate this. I suppose, yeah, you're guaranteed to achieve this for singular point. However, then you could ask, well, can we make it simultaneously visible for all singular points? It's also not obvious, but it can be a guiding principle. And so you could use this freedom, if you wish, as a guiding principle to finding this nice form. And once you have reached that form, I think then you should have very little of this gauge freedom left. And anyway, even if there was something left, for example, even if you have this final form, you could consider further transformations where t is just constant. So if t is just constant, this term would drop, and your transformation would just be a similarity transformation. So that's still some residual freedom, but it just rotates the basis just with some constant matrix. That's not very harmful. So I think that's something one could live with. So the main message is you could use this freedom in some constructive way, trying to get rid of some undesired properties, which you know are just spurious eventually. Yeah, I guess I'm saying that there's a preferred way. Well, I certainly don't know about being clever, but in the next lecture, I'll tell you a way how you can get the preferred choice without really having to think about this. So maybe that will at least in part answer the question. Okay. Now. Right, okay, I think we're basically ready to now apply this, to see how we get the differential equations for some Feynman integrals. So let me start doing that, and then as I say in the third lecture, we can talk more about how we actually get this nice form. The question is, does the D have to be? Does the matrix T have to be invertible for all x? Oh, okay. So in general, I assume that it's invertible up to. I mean, it does. You can write down a t which has some singular points. So in particular, I could write down a t which has some singularity. Let's say at x equals 2, which was never present in the original system, and then I would make a pole appear. So that's certainly something that you could do. I mean, you might ask, why would someone be so mean to do that? But later in what I'm telling you about now, there'll be some algorithms, and if we don't control really what the algorithms are doing, they might just do that. And so then it's our job to get some order into that chaos. Okay, so now let's see how we get the differential equations for actual Feynman integrals. So I will. There's essentially a few main steps that one goes through. I'll mention what the steps are, but then I'll discuss them using an example. So obviously, in a Blackboard lecture, the example will be a one-loop example and relatively unsophisticated. But the good news is, once you really understand in this business, once you understand a one-loop example, I would promise you that actually there's not a big leap to getting to higher loops. Really, then it's rather that the linear algebra increases, as opposed to having matrices that are 3 by 3. You might have matrices that are 100 by 100 or something like this. But there's not too many new conceptual things. So from that point of view, it's really I'd say once you've understood the one loop example, you're ready to go, and you can do. Well, I don't know if you can do Svi's, I don't know how many loops post Minkowskian expansions, but I think you're in a good shape to try. So what are the steps? I'll just have a list here, so just that we don't forget. So that'll be. I'll just mention some names now. It's really like an algorithmic list that one can go through. So there's a number of steps. So the first step will be to define what Feynman integrals are we interested in. So there's a definition of a Feynman integral, which will basically mean draw the graph, and there'll be some associated notion of what we call a family of objects. So I'll say what that is. Then second, it will turn out that this family of objects, they satisfy many relations, and they're so-called integration by parts relations. Integration by parts relations. So they're abbreviated by IBP. That then removes a lot of redundancy, and we arrive at some notion of a basis for the integrals that we want to consider. That basis will be very much like the three integrals we had over there in the toy example. Well, and then once we have this, then we're ready to ask for those basis integrals. Well, how do they vary as we change the kinematic parameters? So then we set up the differential equations for the basis integrals. And then possibly there's a last step. This depends a bit on the answer to the question we had earlier. How good or how bad was a choice of a basis? Are we in need of further rotating it somehow, or did we maybe through some other insight we already chose a good basis? So I will denote this as the choice of a good basis. And so the idea now for this afternoon is that I hope that I can say something about these 3 points. And then this will be most likely will be saved for tomorrow, and that'll allow us to fix this problem of the matrix T. So let's do a really simple example, which however has already some kind of nice details. So So I'll try to go through these points using an example, which is the massive bubble integral. So, so we have some off-shell momentum P, which flows in here, and we could label the loop momentum K like this. And then there's K plus P here and P over there. And I'd like these internal propagators to be massive. So actually, I'll write it now as a formula. So let me define the following object. I call this B for bubble. So what is it? So it's an integral over d-dimensional space, dk. Well, there's some normalization factor I like, but it's not important. So the propagators is minus k squared plus m squared. Anticipating something that will be quite useful, I'll put the power a1 here. And then the other propagator is minus k plus p squared plus m squared. And here we put a power a2. So now we've defined something which depends on these labels a1 and a2. And the kinematics I'd like to call s p squared. It's just easier to write for me. And the other kinematic variable is, or the other variable that this integral depends on is m squared. And implicitly, of course, explicitly here, but it also depends on the dimension d. So the bubble integral then that you're used to, the bubble integral up here, would just correspond to the indices a1 and a2 to be equal to 1. Well, and now with this, it's kind of, I can already say what I meant by integral family. So this is the bubble integral. So let's say you're interested in this integral because it appeared in your Feynman diagram calculation, and you'd like to know what is this function b 1,1. Or maybe that could actually appear in some QFD course, actually. Some example of UV divergences, actually, not so unrealistic. So you'd like to know what this function b 1,1 is. My claim is it's actually useful and interesting to consider this generalization to arbitrary integer values a1 and a2. So generalize to arbitrary, let's say, for the purposes of this presentation, I'll consider the integer. We could also make them negative if you like, a1 and a2. And this already leads me to the notion of the family. So then we would say the family of integrals associated to this bubble graph consists of all integrals b a1, a2 for some a1, a2 integer. Okay, so on the one hand, this is very nice because if we can discuss all these graphs, if for some reason we encounter any of the integrals, we know how to evaluate them. But on the other hand, we've just now made our problem vastly more complicated because we have an infinite number of integrals to consider. So it doesn't sound so good. But this is only temporary because in the second step now, we'll discover that there's lots of relations that are valid between different members of this family, and this will actually take us down again to reasonable and especially finite basis of integrals. And so to see that, it's actually something quite simple. So we need to write down some integration by part relations. So this is the second point. And this is really something absolutely elementary. So the concept is quite simple. So you just say total derivative is 0. So we can write an identity by inserting a total derivative into this integrand. And here on the right-hand side, we just we just reproduce the denominator structure. I don't write it out fully. Now the only thing we need to do, or it's useful to do, is to contract this with some other vector such that we get a scalar quantity. And so we could write down some vector v nu over here. And then we can say that in dimensional regularization, the boundary terms vanish, and therefore this total derivative just gives us 0. So that is pretty easy to obtain some relation. But now we can just use the chain rule and work out what this actually means. So you see the derivative, it can hit the denominator here over here. It will increase the power, and then we'll get some scalar product, whatever the argument was here. For example, we get k or k plus p. This will be a scalar product with v, and then we can work it out what the answer is. For example, you could choose. So it's not so useful to have just an arbitrary v. We could choose something specific. We could choose v to be equal to the external momentum p, or we could also make it equal to k. In the second case, then we'd also have to consider that that the derivative can hit this k. Anyway, it's a simple algebra, and I'll just write one of the two relations that you get. So you have 0 equal. So there's some terms where we just get the integral with indices a1, a2 back. So that, for example, is the case if we choose v equals k and this derivative hits here, then we just get the term d times b. And there's other terms which have to do with this algebra I just mentioned. There's minus a2 b of a1 minus 1, a2 plus 1. And then there's two further terms. There's plus There's plus 2 times m squared a1, b a1 plus 1 a2 plus 2 times m squared minus s times a2 and then b of a1 a2 plus 1. All right. So I believe this was, yeah, that came from the choice v equals k. Now you could do the other calculation as well. So there's a second relation. You can actually save some time by noticing that the integral b, if you just look at the graph, there's some symmetry as you swap the lines. So in other words, you could do some relabeling of loop momentum, which flips a1 and a2. So you can get a second relationship, a second identity simply from using that symmetry by saying b of a1, a2 is the same as b of a2, a1. So therefore you don't have to do the other calculation. Okay. So now how does this help us? You see that I've organized the terms in this equation in some systematic way. Namely, in the first line, if you sum the indices of the function b, it's equal to a1 plus a2. While in the second line, the sum is a1 plus a2 plus 1 in all the terms. So there's some kind of hierarchy. And so if you imagine that we have some integral with higher values of the a's, we could now systematically use these two equations to reduce the sum of the indices. And so in this way, you could think of some of some graph where you have all the tuples a1, a2, and if you have the higher ones, you can gradually reduce them to the lower ones. And as a result, so then there's something special if one of them hits 0, then you see some of the terms in the equation can become singular, so it will stop there. And the upshot is that you can reduce all the indices just to the point where they're either 0 or 1. And that's great because it means that we can essentially forget about the integrals with the higher indices, and we just then need to know about the ones with indices 1 and 0. So let's make some space. So it turns out that all v a1, a2 can be reduced. Reduced is some kind of slang in this community, so they can be related to other integrals, to only two integrals. And these integrals, we can choose them, for example, to be b10 and b1,1. And so then we could speak that there's a basis consisting of these two integrals. So in the community, some people call these master integrals. So this is also a common way of talking about them. It's absolutely fine. I just personally prefer the word basis, because when you say basis, you're kind of very conscious that it's a choice which basis to choose, and you might want to change it. While master integral sounds somehow very absolute to me. And that has actually led to quite a bit of suffering in the community, I believe. So anyway, for that reason, I prefer the word basis, but of course, feel free to. I myself also use master integrals, never mind. So what does it mean concretely? I've said it, but just to make it very explicit, if you have any such integral b a1, a2, then it can be written as a linear combination of these basis integrals, where, of course, the C1 and C2, they can depend on, of course, what initial values you had here. So, for example, let's be very explicit, and that will actually be useful later. Let's say we had an integral b0, 2,0. In this case, actually, this part is 0, and we just have a coefficient C2, which is epsilon divided by m squared times b1,0. Just as before, I'm using d is equal to what am I actually doing? No, actually, it's good. So here I choose this d. We'll see a bit later why that's useful, but it doesn't really matter. You could go back to d if you prefer to. And let me give another example that will be useful later. So b2, 2,1. That becomes epsilon divided by m squared 4m squared minus s b 0,1 plus 1 plus 2 epsilon 4m squared minus s b 1,1. So I think these two equations, actually, they give an illustration to something that was asked earlier from up there. So you see, this was one basis choice, but we could have equivalently chosen the basis of those two integrals. And then the transformation matrix T is exactly given by the coefficients here. And now we see what it is. Well, it's invertible. We can check it. And we see there's some epsilon dependence. There's some poles. These actually happen to be all physical poles, so here we're lucky. It's not too bad, but so this is quite typical that you can already anticipate that this would rather change the differential equations that we get then. Okay. Right, I think now we're actually all set to get the differential equations. There's nothing that prevents us from it. So let's compute them. Well, so differential equations in what? So what do the integrals depend on? They depend on the parameter s and on m squared. So we could actually we have two choices. We can consider these two partial derivatives. We'll actually see later that they're related. The reason is that the integrals, they have some scaling property, or in other words, you can do dimensional analysis. If you know the dependence on m, then equivalently you know the dependence on s. So that we'll see in a minute. But since it's a bit easier, therefore we'll focus on getting the differential equations for M. And why is it easy? Well, so we start with our basis, and we just want to compute this partial derivative. So now just imagine how would you do this? What would be the effect on these integrals b? Well, m squared just appears in two places. It's just a case of using the chain rule. So nothing complicated. So we have that dm squared on b a1 a2 is equal to, we get one term where the derivative hits the first propagator and increases the power by 1. And we have another term where it hits the second propagator. So really very simple. But now you see here, we get exactly, well, actually, let me just write it out. So this is minus b2, 0. In this case, we get two terms, b2, 1 and b1, 2. But we know that there's a symmetry, so we can just write it as minus twice b2, 1. So we have something quite useful, but now these, well, these are different integrals than the ones we started with, so that's not yet the final form of our equations. So we need to rewrite these two integrals again in the basis. But that's exactly the relations that we worked out over here. So we just need to plug it in, and we get our differential equation matrix. So let me just write it over here. So we plug it in, and we can organize it in the following way. So we get a first matrix 0, 0, 0, minus 2 divided by 4m squared minus s. And then there's a term plus epsilon. This is not yet so meaningful how I'm organizing them, but it's just a neat way of writing down the equations. 0 minus 2 divided by m squared, 4m squared minus s. And then there's a minus 4, 4m squared minus s. And let's close the bracket. And here we have again our initial basis, E1, 0, E1, 1. Okay. So what do we see? It looks like the equation is not so bad. It's actually almost what we wanted. For example, we see on the right-hand side some poles for m squared minus s, m squared. If you think a little bit about the physics of this bubble integral, you might say, okay, that's actually something reasonable. So we can be quite happy. And also, so if we think about it further, so m squared is a variable, so it's really just a single pole. It's not worse than anything that we expected. There's no spurious singularity in that sense. One thing that is not yet as in our toy example is the epsilon dependence. It's not too bad, but it's actually linear in epsilon, and it's not proportional to epsilon. So had I claimed in the beginning that we can get a form which is just factorized in epsilon, then we haven't achieved it yet. And so that's something that would be actually very nice to get. So let's see. I'm just looking at the clock to see what would be a good way of. Yeah. Yeah, very good. I think what I'll do is I'll show you how we can get to this nice form that we like, and then I'll motivate next time how we did it. So so two things. One, I said this in words. We could have equivalently written down the differential equation in S. You can derive it. So you can derive the ds derivative in the same way. But it actually does not give you new information. So it's fixed by fixed by dimensional analysis. So what does it mean? It means that if we rescale all dimensional full variables, and this is done by the following operator, S ds plus m squared dm squared, then this is an operator that just counts the dimension of your integral. And that's something you can just read off from dimensional analysis. So concretely, when you apply this to the basis, or for that matter to any integral with any indices here, it just has to reproduce the integral itself times some value, which is the dimensionality of the integral. So in other words, we're guaranteed for this to be some diagonal matrix. We're guaranteed for this to be some diagonal matrix, where in the diagonal you just have the dimension of the integral. And let's just see what it is. So for this power here, we get minus epsilon. And here you see we have one more propagator, so we get another minus 1 minus epsilon. So this is just what you would get by power counting for the integrals. So what's the upshot here? You already know in advance what the ds derivative is going to give. However, as my students will confirm to you, it's very useful to implement it. Just by all means, if you're doing such a calculation, it's a bit of extra algebra. Just do it, and then you'll be very happy to find this relation. And you know, in 1 out of 10 cases, maybe it reveals that there was actually some problem, and you're happy to find it in this easy way. So this is just as a general remark in this game. If there's a simple consistency check, then better do it. It's absolutely worth the extra half hour so that it takes you to implement it. Okay, now yeah, I don't want to go over time, so I think what I'll do, I'll now just write down the transformation matrix. No sense in writing down many other matrices, what that leads to. And well, if you're curious, you can also already try it. But so I'll write down the transformation matrix. And then we'll figure out next time why that leads to something nice. So let me just see that I do it right. So did we give this a name? Yeah, so I want to, so we want to get to the canonical F. So we'll say F is some transformation matrix times the basis we've been considering so far. I think writing it this way is probably the inverse of what I was talking about before, but I hope it's not too confusing. And actually it turns out that only something very simple is needed. We have actually a triangular matrix where I need a little bit of space, sorry. So in the lower right we have square root of minus s times 4m squared minus s. And there we have a b 1 0, b 1 1. And so just to be clear, in the language that we were using before, this would be the T inverse, but since it's a diagonal matrix, it's particularly easy to diagonalize it, to invert it. So I will stop here. The claim is that if we do this transformation on this matrix A, then we find something that I would call a canonical form, which is not exactly what we had this morning, but it has the main features of what we had this morning. And so that will essentially tell us what is the relevant function space, what is the symbol alphabet that Lances was talking about, and it will be in that form that we can solve the equations in principle to any order in epsilon. And so next time we'll actually understand a bit better why this is actually a good choice. We can understand it from the differential equations, but actually there's a nicer way where you start just looking at the loop integrands And we're going to do some analysis which is very similar to generalized unitarity, where we discover, in particular, these factors here in the matrices just from an integrand analysis. So yeah, I think it's a good moment to stop. Thanks a lot for your attention.
Thank you, Johannes. Please, questions?
Can we understand the redundancy in the data contained in the ds and the dm squared derivatives by saying in the functions you always have to have dimensionless ratios appear, so we'll end up with things like s over m squared or something like this?
Yes, that's exactly correct. So the question was, can one understand the redundancy in S and M squared by saying that the functions really only depend on a dimensionless ratio? That's exactly what's happening. So for example, another way of interpreting the first line would be to say the function b, let me take the second one because it's a bit more interesting. So the way we're talking about it depends on m squared and s. Now this equation tells us that the dimensionality is -1 minus epsilon. In other words, we could write it as s to the -1 minus epsilon, and then we'd have a new function, let me call it g, and that function would then just be a function of the dimensionless ratio, as you say, s over m squared. And so in other words, the scaling operator sds plus m squared dm squared acting on any function of a dimensionless ratio just gives 0.
If I've got an amplitude that after IBP reduction depends on masters from multiple integral families, is it better to have a different differential equation system for each family or put it all into one big system?
Right. Okay. So the question is, let's say we have different types of Feynman diagrams, and we do this IBP reduction, and we kind of have a joint system of master integrals. Is it better to treat them all in one go, or better to treat them separately? Hard to answer that in general. I would say, I mean, sometimes it's very nice to have a setup where one can treat all integrals in one go. For example, in some projects where we are dealing exclusively with planar integrals, it's particularly easy to do that, to combine all of the integrals. And it can streamline certain calculations. For example, when you think about boundary conditions, it's then very easy to map one integral to another and see that the boundary conditions are the same. And so in that sense, it can save a lot of work. So I would say if it doesn't place a big constraint on your computing time, on the amount of memory computers need, then by all means do it. Otherwise, so the flip side is if you're doing really very complicated calculations where maybe the running time is extremely large, it might also make sense to separate them. But I think it's really case by case what's the best. Thank you.
Maybe just to comment on that question earlier about whether the discontinuity satisfies the differential equation. I mean, if you look at that kind of differential equation on the upper left and you apply the discontinuity to it, then these matrices on the explicit matrices are meromorphic, so they don't have any discontinuity. So you just get the discontinuity on the far right. And then on the left-hand side, you just have to be able to pass the discontinuity past the derivative, and I think it's pretty easy to see that should always should hold pretty generally. So I think, yeah, that's a pretty general way to see it should work. And maybe one other just remark is that in the bubble integral, the fact that you got this differential equation, there was one thing you maybe needed to use implicitly, which was that there were no sort of irreducible numerators. In other words, the dot product of external and loop momentum was just a difference of propagators.
Yes, that's absolutely correct.
Quite hold when you go to two loops, but otherwise,
that's absolutely correct. So you're absolutely right to point out. I advertise, of course, that understanding one loop gets one ready to almost do all loops, but there are a few important technical points, and so in particular, when defining the family of master integrals, Lance is right to point out that there are certain things called irreducible numerators. So when one includes in the family not only the denominator factors, but also certain numerator factors become important, and one has to take them into account. But it's done in a similar way to what we've done here. But that's certainly an important new feature in loop calculations, in multi-loop calculations.
Just following what Lance was saying, this means that a counterexample on the discontinuity is if we put a logarithm in front of the f. So if we don't have meromorphic functions in this system of differential equations, it doesn't work.
So the equations we get here, maybe it's actually a good thing to point out. So these IBP relations, you see, they're actually they don't even have poles. So the poles only came about over there when we solved for some integrals in terms of other ones. But originally they're really just polynomial in the variables. Then here they become rational functions. So that implies that the differential equations that we write down, likewise, like we see it's put in evidence here by this matrix A, it's really just a rational function. And it's kind of interesting then, and this will be a part of discussion tomorrow, that here it's our choice actually. You see something interesting happens here in this transformation I wrote down, whereas for the first time a slightly more non-trivial function, a square root that appears, but this is our choice to introduce it, and it's a bit of a trade-off. We lose the fact that the right-hand side here is just a rational function. It will become algebraic function. We lose that property, but then we gain that the epsilon will be factorized on the right-hand side. But in general, unless we make some funny choices and introduce ourselves some logarithms or other functions, the right-hand side of the differential equations is rational.
For the IBP relation, in that equation, if we have some numerators, do we have to be very careful because the current might not vanish sufficiently fast at the infinity?
Yes, okay, that's a very good point. In what we've been discussing within the context of dimensional regularization, we can argue that the boundary terms should vanish, and therefore then you do not have to be careful. However, it's very interesting to think about, in my view, it's very interesting also to think about what happens for finite four-dimensional integrals, for example, because that would be much closer related to what we had this morning, that at the end of the day, we are not interested in this whole epsilon expansion. We may want to just know the finite functions as they depend on the kinematic data. And in that case, one has to be rather careful. So then the similar steps also hold, but for example, what you may have to be careful about when you differentiate is whether or not you produce contact terms in your IBP relations. So what I have in mind, for example, here we have massive propagators, so we'd still be fine, but you might have something like the Laplace equation, that if you have Laplace operator in k acting on 1 over k squared, you could find then a delta function. And so if we have massless propagators and an integer dimension, then such things can happen. And again, it's a bit of a trade-off, because if we do have finite integrals, there's some advantage in sticking to them and not using DIMREG, but then we have to be a bit more careful. So it's a very interesting point indeed, and important in these considerations.
So why in DIMREG it always vanish?
Why in DIMREG? Well, I guess in the end of the day, it's it goes back to the very definition of DIMREG that I think it's also related to it's eventually related to the fact that I think it's ultimately it's some analytic continuation argument. Yeah. Mm.
Thank you.
I don't see any other questions. So let us thank Johannes one more time. So this is still not over. There is a cinema. Christoph is leaving, but I hope you know. I was hoping for some announcement, but I will have an important announcement about tomorrow. Tomorrow is a special day because it's Saturday. If you were asking what that lady is doing here on the reception, we will find out she is very important because even though, yeah. So the building will be locked for Saturday and Sunday. So I have a card to enter the building, but it will, as a default, it is locked. So we have to find some way to get in. I don't know yet how to do it because, as I said, the lady is important, but she is not here. So if you are desperate, you can wave here. So we can open that door. If you are really desperate, you can wave here, and the speaker can open the door. Yeah, there should be always someone. I don't want to let the door open like with some, because yeah, there are strange people. There might be strange people around, and we don't want them to hear. Oh, we might want to, yeah. So this will be one problem for tomorrow, but I hope we will cope with that and we will manage. And of course, as you heard, it will be a long day. We will try to provide, for example, this pizza. We will see how, but it is us. There is still lunch and break as we had it so far. But for the pizza, it is us. We have to organize it. So let's hope it will work. And yeah, so Christoph is not here, so I hope you know what is on the. Yeah, I should probably switch off the